Hi, and welcome to Mr. Carroll's classroom. Today we're going to talk about solving exponential and logarithmic equations that have the same base on both sides and the same structure. So let's go ahead and check it out. Okay, so here I have two of our generic examples. The top is an exponential equation in which we have the same base and the same structure on both sides. So the base of b to the m power is equal to the base of b to the n power. So if you end up with something like this, and b can be any base, and this m and m could be any exponent, but as long as they have the same base on both sides, then that infers that these two exponents must be equal to each other. M must be equal to n, otherwise this will not work out. So what we can do is we can take those corresponding parts, set them equal to each other, and solve. All right, and then also below here we have a logarithmic equation. Log base b of m is equal to log base b of n, which means that, well, we have the same structure on both sides, the same base. Really the only difference is m and n, which means that m must be equal to n in order for this to work out. So we could go ahead and write it as m is equal to n. Now, while we're doing this, because I'm going to show you how to do this by demoing it, we'll have a few examples because it might be kind of unclear what we're actually talking about here. There's two things I want to mention. So number one is that even though we're using this process where it's going to kind of cut out a few steps, it's going to make it a little bit easier to solve, you do have to go back and check your restrictions, okay? So for example, this one below here, where we have logarithms, if I am solving for these two that are, the m and n that are inside of that logarithm, neither of those could be 0 or negative. They have to be positive, right? Because we can't take the logarithm of a negative or a 0, right? However, if I'm solving for the one up top, then there are no restrictions up here. So we just have to go back. We just have to remember, go back and check your restrictions. Also, just because we're going to use this little, it's not really a trick, but we're going to rewrite these equations to have the same base if we can. That doesn't mean you can't just solve them using your traditional algebra by applying your inverses as usual, okay? So that will always work. It's just that in these particular instances, you will notice if we can write them as the same base, then it can basically make it easier to solve. Okay, so let's go ahead and take a look at what we're actually talking about. All right, so there's going to be three examples here, and here's the first one. So the first one, we have 36 to the fourth power is equal to 6 to the 3x plus 2. The issue is that, well, these don't actually have the same base. However, if you notice, we can rewrite, let me go ahead and label this. We can actually take, we can actually rewrite both of these bases to be identical. Okay, so this one is 6 over here. This 36, I could actually rewrite this as 6 squared. 6 squared is 36, so I'm going to go ahead and put that inside of there. All right, so the 36 is 6 squared, all to the fourth power, which is equal to 6 over here to the 3x plus 2. So that side hasn't changed at all. All right, now what do we do when we have 6 to the power of 2 to the power of 4? Well, based on our exponential properties, we multiply those two numbers. So 2 times 4. So that it means that we have 6 to the 8th power is equal to 6 to the 3x plus 2. Right, and now you can see that these clearly have the same base, which means that these exponents, since these have the same structure, meaning there's just an exponential on the left and one exponential on the right, and they have the same base, that means those exponents must be equivalent, meaning I can drop them down and say, well, the 8 must be equal to the 3x plus 2. All right, and now all of a sudden this got pretty easy to solve, right? I'm just going to subtract 2, meaning I have 6 on the left is equal to 3x, divide both sides by 3, so I get 2 is equal to x. All right, now let's just go ahead and back and double check here at our original. Are there any restrictions that need to be placed? Well, no, not in this case because we're talking about exponentials, so there are no restrictions. So x is equal to 2. All right, okay, let's try another one. This one's slightly more complicated. I have 1/16 to the 3x plus 1 is equal to 64 to the x plus 4. So there are really a couple of different options to rewrite these insides here as a common base. The first option I would say is probably a base of 2. This 1/16, let me just rewrite these here. This 1/16 could be rewritten as 2 to the negative 4th. That would be 2 to the negative 4th would be 1 over 2 to the 4th, or 1/16. Which also, this 64 could be rewritten as 2 to the 6th. Now, I'm actually not going to use 2 to the negative 4th and 2 to the 6th because there are other options for bases that will make these numbers smaller, essentially. And so I'm always going to do that if I can. You will end up with the same exact answer. It doesn't really matter which one you choose, but I'm just trying to make it easier. So another option for 1/16 would be 4 to the negative second power. That would be 1/16, 1 over 4 squared. And also 64 is 4 cubed. Okay, and so don't forget about our exponents out here, this 3x plus 1 and our x plus 4. And so now I'm going to multiply those exponents, because 4 to the negative 2 to the 3x plus 1 is the same thing as 4 to the negative 2 times 3x plus 1. And this is the same thing as 4 to the 3 times x plus 4 by multiplying out these exponents. So let's go ahead and actually distribute these now. So I'm going to distribute that negative 2 in, which means that I have 4 to the negative 6 minus 2. I'm sorry, whoops, minus 6x minus 2 is equal to 4 to the 3x plus 12. And so now here you can see I have the corresponding base, the same base, right? All to the to some kind of exponent, which means those exponents must be equivalent. Okay, so let's go ahead and set those exponents equal to each other. So that means negative 6x minus 2 is equal to 3x plus 12. And from here, it's just a matter of simplifying. Excuse me. So let's see here. I'm going to add 6x to the right-hand side. So that means I have 9x. I'm going to subtract this 12 over. So it's negative 14. Negative 2 minus 12 is negative 14. And then I'm going to divide both sides by 9, which means that negative 14 over 9 is equal to x. And just double checking for restrictions, this is an exponential equation, so there are no restrictions here. All right, so yeah, x is equal to negative 14 over 9. And you can double check. You can plug that in, and you will get two equivalent sides. All right, let's do one more. And this one is going to be a logarithmic equation. And I also chose this one specifically because this left-hand side does not have the same structure as the right-hand side. Now, luckily, all of these logarithms do have base 7. So if I could somehow get this left-hand side into one logarithm, then both sides would have the same structure, and I could set the insides equal. Well, luckily, through exponential and logarithmic properties, if I have the addition of two logs that have the same base, then I can combine them by multiplying the insides together. So that means the left-hand side will be log base 7 of x times, the one on the left, times the 3x plus 5. And that's all equal to log base 7 of 2. Excuse me. All right, so now I do have the same structure on the left-hand side and the right-hand side. Log base 7 of something is equal to log base 7 of something else. So I can go ahead and set those corresponding parts equal to each other. So I have x times 3x plus 5 is equal to 2. And now let's go ahead and solve this. So I'm going to distribute this x, getting 3x squared plus 5x is equal to 2. And now this is a quadratic, and in order to solve a quadratic, we always set it equal to 0, and then we try to factor if we can. If we can't factor, then we can always use the quadratic formula. But let's go ahead and set it equal to 0 and see if we can factor it. So I have 3x squared plus 5x minus 2 is equal to 0 by subtracting that 2 over. And then I'm going to go ahead and I'm going to factor this by guess and check. So since I have 3x squared, then the first terms have to be 3x and x. And so since I have negative 2 here, that means basically this can either be 2 and 1 or 1 and 2, vice versa. And also, since it's a negative, this has to be plus and minus, or vice versa, minus and plus. So how do I figure this out? Well, basically, I know that after I'm done with this, then when I multiply these two outsides and then add the multiplication of these two insides, then I should end up getting positive 5x, which means taking our factors from negative 2, that means I'm going to have x plus 2 on this side and 3x minus 1 on this side. And again, this would mean that I'd have 3x times 2, which is 6x, minus 1x, which is positive 5x. Okay, so guess and check did work. And now I have 3x minus 1 times x plus 2, so the factored form is equal to 0. So I can set each factor equal to 0. So 3x minus 1 is equal to 0, and x plus 2 is equal to 0, and then solve for x for each one of these. So x is equal to, add 1, divide by 3, so positive 1/3, and subtract 2, so x is equal to negative 2. And now you're going to see here where we do have some extraneous solutions. In fact, this one right here, if I plug x is equal to negative 2, then this one would be the logarithm of a negative number. This also would be the logarithm of a negative number. 3 times negative 2 is negative 6. Plus 5 is negative 1. So no, this one will not work. X is equal to negative 2 is an extraneous solution. However, x is equal to positive 1/3 does work in this case. So we have a one actual solution from our two candidates. Okay. All right, guys. So there you go. There's a quick lesson on how to solve exponential and logarithmic equations. If you can rewrite them as the same base with the same structure, then you can set those corresponding parts equal to each other and then solve algebraically like you normally would. So hopefully you found this lesson useful, and I hope to see you in the next one. Bye now.